Okay, in this video I'm going to continue on with exercise 5C of the book Fundamental Applied Mathematics. We're on page number 140 and this is question 9. So if you haven't done it yet, I'd suggest you do questions 7 and 6 and maybe look at my videos on 4 and 2 as well. But basically definitely 6 and 7, they built up all the things you need to do in order to solve this question. Now, I'm assuming what you know at this stage is that doing these inclined and connected particle questions, your diagrams are very busy and there are a lot of things in them. However, they're not actually very complicated. They're not very difficult to understand. So I've drawn the diagram in front. I've drawn in the relevant forces. So as I call out the question, you can look at those and perhaps make sense. I want you to notice something, of course, that my xy plane, okay, corresponds to my I hat and j hat unit vectors. My x prime y prime plane on the incline corresponds to my I hat prime and j hat prime unit vectors. So the question reads like so: a diagram shows 5 kilogram particle on a slope of 3 and 5, an 8 kilogram particle on a horizontal table, and a 20 kilogram particle hanging freely. They are all connected by two light inextensible strings passing over smooth pulleys. Find the common acceleration of the masses, initially when all surfaces are smooth, and secondly if all surfaces are rough with a co-friction of 1/4. So before I continue, just to note something, we're saying that it's 3 in 5. So if I say my angle here, so sine A is equal to 3/5. That's what that means. So of course the cosine A is going to be equal to 4/5, and the tan of A is going to be equal to 3/4. Alright, but look, that's something you're well used to at this stage. So the forces I've put in, we have two strings, so two tensional forces. The first one I'm going to call T1. It's going upwards, so it's in a positive j direction, and this one is going horizontally in a positive I direction. We have the weight of the 20 kilogram particle, which I'm going to call W1. It's in a negative j direction, so it's going to be equal to negative 20g times the j hat unit vector direction. Of course, because gravity is like this. Same principle is applied here for the weight of the 8 kilogram particle. It's normal vector. I'm just going to call N2, and it's in a positive j direction. Secondly, we have a second string here, and similarly it's a T2 this time. This vector here is going in a negative I direction. That's where the negative comes from. And this one here is going in a positive I hat prime direction. Okay, so it's on the I hat, or x prime y prime plane this time. So all of these are on the xy plane, and the incline is on the x prime y prime plane. So it's got a different unit vector here. The normal vector is just, I'm going to call it not N2, I'm going to call it N3, and that's in a j hat prime direction. N3 in a j hat prime direction. The weight vector, of course, is in a j hat direction. Okay, but we want to be able to put this into the x prime y prime plane as normal. Something we've done countless times at this stage. So the only resolving of vectors that needs, or resolution, excuse me, of vectors that needs to be done here is the weight vector. So I'll just rub out these lines because we don't need them anymore. Alright, just to free up the diagram a small bit here. Alright, so we need to resolve this vector, this weight vector here, number 3. So we draw a parallel to the y prime, we draw a parallel to the x prime. They're at right angles, and they must be going in these directions here. Alright, so just get rid of this because that's not needed anymore. So this vector, or this angle here, is A as well, because it bisects the angle A at right angles, which that's perfect. So we're going to get, this one is going to be negative 5g times the sine of A. And we said the sine of A was 3/5, so it's going to be 3/5, and this is in an I hat prime direction, and it's negative. And this one here is going to be negative 5g times 4/5 j hat prime. So just to kind of write it very explicitly, the weight vector of 3 is going to be equal to negative 3g I hat prime, negative 4g j hat prime. Alright, that's pretty straightforward there. So I'm just getting rid of these because we don't want to clog up our diagram. So W3 sub x and W3 sub y. Alright, so just let me note this here. W3 is equal to negative 3g I hat negative 4g j hat, and they're both in the prime direction. Alright, so I know that the diagram looks very busy, but I hope that you're understanding this, because the principles and the mechanism hasn't changed. The mechanics of it has not changed. So all I'm going to do now is solve this. So I'm going to solve it by looking at Newton's second law on the 8 kilogram particle, Newton's second law on the 20 kilogram particle, and Newton's second law on the 50 kilogram particle. And the unit vectors I'm going to use are, for these two over here, I'm going to use the I hat, j hat unit vectors, and for this one it's going to be the I hat prime, j hat prime unit vectors. Alright, because this rotational coordinates, it's quite straightforward. So let's look at the 5 kilogram particle first. So let's go, the sum of the forces, force vectors, is equal to the mass times the acceleration vector. So of course, because we know that the particle isn't being lifted off the ground, there's no point even doing the j's, because it's just going to tell us what n3 is equal to. So n3 is just going to be equal to w3. So let's go about the I hat prime direction. So we're going to get t2 I hat prime minus 0, because there's nothing else there, is equal to the mass, which is 5, times the acceleration vector. So let's just decide which way we think the whole thing is going to go. And it doesn't matter, just pick one and you'll find out later on whether or not you're correct or whether you're incorrect. So I'm going to say we're going in an a I hat prime here, we're going in an a I hat this way, and we're going in a negative a j hat this way. Alright, so it's the same acceleration, and I've just put on the different unit vectors. So this time we're moving in a 5 times a I hat prime. So if this is equation 1, equation 2 is, that's incorrect. That's very incorrect, because I forgot about the weight vector. So let's go back here. We got to take away from it w3, which was 3g I hat prime, and that's equal to the mass, which was 5 times a I hat prime. So we know that t2 minus 3g is equal to 5a. Alright, so yeah, sorry about the fact that I left this out there. That's just, it's difficult to do these videos and to think at the same time. Alright, so that's pretty good. Next, let's apply the same mechanics to the 8 kilogram particle. Alright, so like I said before, if you do the j hat direction, you're just going to find out what the normal vector is. And that doesn't matter, because we're not being lifted from the ground or the horizontal. So that means that t1 I hat minus t2 I hat is equal to the mass, which is 8, times a I hat. So equation 3 says t1 minus t2 is equal to 8a. Alright, that was very straightforward. And finally, let's apply the same thing onto the 20 kilogram particle, whereby we get t1 j hat minus 20g j hat is equal to the mass, which is 20, times negative a j hat. So we get equation 4, t1 minus 20g is equal to negative 20a. Alright, so that's very straightforward. Just like I said, the diagram does look busy, and there's no real way around it. Like, you could split each of these into 3 different diagrams, but I find that you'll be at it a lot longer than you need to do. So let's going to push this up here, and the next thing we're going to do is solve this set of equations. So let's see what we can do here. Well, I can get rid of this equation, because we've used that. So we have 3 equations and we have 3 unknowns. So we need, for every unknown you need 1 equation, so we can solve this set of equations. So how did you go about doing this? It's there are loads of ways. So how about we do the following? How about we get everything in terms of a and g and plug them into the third equation. So that means from equation 2 we get that t2 is equal to 5a plus 3g, and from equation 4 we find that t1 is equal to 20g minus 20a. So I'm going to rename those, relabel those equations to be number 5 and number 6. So if I plug 5 and 6 into equation 3, we'll get 20g minus 20a minus 5a plus 3g is equal to 8a. Therefore 20g minus 20a minus 5a minus 3g is equal to 8a. So that becomes there, that's 17g plus 17g. This is negative 25a, bring on the other side, and we get is equal to positive 33a. Therefore a is equal to 17g over 33. So we asked to find out the the common acceleration of all the particles. So what I'm going to do is just go to the back of the book and check the answer. So just bear with me one moment there now. So we're on 5C question 9. 5C question 9, 17g over 33, and that is correct. That's perfect. Alright, so let me look now and see if I can just take any other ones while I'm here. Okay, the next one should be 14g over 33. Alright, so 14g over 33. So that's correct, and that's pretty straightforward stuff. So the next thing we're asked is, what happens if all surfaces are rough with a coefficient of friction of 1/4? What do we do here? Now we could of course go back to the very start, but it's quicker if you don't do that. So you just need to think about it a small bit. If I'm adding a coefficient of friction, well, what happens? So first of all, just let me go back down here in actual fact. We know that the frictional force is equal to the normal force times the coefficient of friction. Alright, so that means the following. It means for the 8 kilogram particle that the friction is going to be 8g times the coefficient of friction, which is 1/4, and that's going to be equal to 2g. And for the 5 kilogram particle, it's going to be 5g, which is that's the weight on the normal force times 1/4, and you're going to get 5g over 4. Alright, so let's just put those straight in here. There's my frictional force here. It's negative 5g over 4 I hat prime. And this one here is just negative 2g I hat. Now we're getting very mixed up here. Alright, so they're the only two things we've added. So instead of going straight back to the drawing board with our Newton's second law equations down here, well, let's just add in what we need to do here. So okay, for the 2g, that goes onto this equation here, so it's actually T1 minus 2g minus T2 is equal to 8a, so this is equation 3. And then for the 5 kilogram particle, that's this equation here. We just need to tag in this negative 5g over 4. So you have T2 minus 5g over 4. And that's equation 1, like so. Alright, so that was pretty straightforward, and the rest is just doing the exact same thing as we did for the first part. So let's get that equation. We'll say equation 5 says, look at equation 1, we have T2 is equal to 5a plus 3g plus 5g over 4, and equation 6, I'm going to take that from here. It's going to be that T1 is equal to 20g minus 20a. So let's plug equations 5 and 6 into equation 3. And what do we get? We get 20g minus 20a. We have minus 2g. We have minus 5a minus 3g minus 5g over 4 is equal to 8a. So let's just multiply across by 4. 4 2s are 8, so we get 80g minus 80a minus 8g minus 20a minus 12g minus 5g is equal to 4 8s are 32a. So let's just rearrange this. So 80g minus 8g is 72. That becomes minus 60 minus 55g. And we get on the other side 80, well, negative 80, that's negative 100. Negative 100 becomes 132a over here. There a is equal to negative 55g over 33. Oh, sorry, not 33, 132. So I don't know. Can we fix this now? So what if we divide 133 by 30, or 132 by 33? 4 times, and let me see now. 55 divided by 14. No, 4 times, just under 4 times. What if I divide the whole thing by 4? I'm just trying to just put it in the form that the answer is. Actually, you know what the best thing to do is just look at the decimals. So the answer in the book is that it's 14 multiplied by 9.81 divided by 33. So the answer in the book says the answer is 4.16. And I say that it's 55 multiplied by 9.81 divided by 132, and we get an answer 4.08. 0.08. Alright, so they're pretty close. They're very close, in fact. So that's that. Thanks for watching. Please pass it on to your friends and subscribe to my channel.